Alright, so what we're working on today is exponent properties. And just to be clear, I had this little diagram up here. This right here is called a variable. The number in front of your variable is called a coefficient. Even if there is no number in front of here, there is a coefficient of 1. This is called the exponent of power. I'm going to say power probably a lot, or exponent a lot, so you know what I'm talking about. The variable here, not the 2, but the x here is also known as the base. So I'll say base several times. A base has an exponent. And so pretty much everything has an exponent, at least of 1. Alright, so what I want to get into is some of these properties. And so that's what we'll do as we get ready to get started. Alright, so we have our properties of exponents here. And we're going to start off with the product of powers. So I'm going to take a look at these as we move. Alright, let's get into it. The product of powers simply says if you have I wasn't scratching, digging in my nose, so don't be saying I was. Two things being multiplied, that's a big multiplier dot there. You multiply them by adding the exponent. Okay? That's the property. Here's an example. An example of that would be 7 squared times 7 to the third power, and that equals 7 to the fifth. 2 plus 3 is 5. Another example would be if I had something like 3x times 2x to the third power. Now normally you wouldn't see the times like that, you would see parentheses, so that means the same thing. I just wrote a dot there. But this would equal 6. Why? Because 2 times 3 is 6. X to the first times x to the third is x to the fourth. Okay? So I added those because I was multiplying them. Alright? The next property is a power to a power. If you have something with an exponent raised to another exponent, notice you have two exponents there, m and n, that equals x to the mn, which means multiply there. Alright, an example of a problem like that would be if I had 8 squared to the third power. 8 squared raised to the third power is not 8 to the fifth, but 8 to the sixth, because you multiply in a situation like that. Alright, another example would be x to the fourth raised to the eighth. That equals x to the 32nd, because you multiply. Alright? Let's keep moving. Power of a product. The power of a product simply says that you have x and y to the m. That means x to the m and y to the m. That simply says that this outside exponent is multiplied or raised to each exponent. Not to the base, but to the exponent. So an example would be if I had 7x squared raised to the second power. That really means 7 squared and x squared squared, but I can go ahead and make that 49x to the fourth. 7 squared is small enough. Up there when I had 7 to the fifth, that was just a big number. I didn't change it. Neither did I change that. Alright. Another example of the power of a product would be if I had something to the effect of x, y, z, and say that was the power of 2 and that was the power of 4, and then I raised that to the 7th power. Now remember that the exponent here is a 1, even though it's not written. And if you haven't noticed yet, I'm still using the power of a power because all of these are inside a parenthesis being raised to another exponent, just like this said. So this is actually going to be x to the 7th. Why? Because 1 times 7 is 7. Y to the 14th. And z to the 28th. 7 times each one of those exponents. Alright? Now, negative exponent we'll come back to in a second. I want to jump down here to some of these because I think these will help explain negative exponent. 0 exponent says anytime you have anything to the 0 power, it equals 1. An example of this would be 7 to the 0 equals 1. Another example would be if I had 5y cubed to the 0 power, that still equals 1. Notice how everything is raised to the 0 power. However, if I gave you this problem, I'm going to write this one over here. If I said 5y to the 0 power, this equals 5. Why is that? Because y to the 0 power, this equals 1. So it's really 5 times 1 equals 5. Alright? Now the next thing is quotient of powers. And this simply says, in the case of dividing and you have the same base, okay? You're dividing and you have the same base. You divide by subtracting. You have to subtract in that order. Top exponent minus the bottom exponent. Alright? So an example of this would be if I had 7 to the 6th divided by 7 to the 3rd. 6 minus 3 is 3. Notice I don't divide the 7s to get 1. You just subtract the top and the bottom, but in the order of top minus bottom, exponent that is. Another example would be if I had y to the 10th divided by y. Remember, that's really y to the 1st power, so this will equal y to the 9th. Now, power of a quotient simply states that if you have x over y, and that's raised to an exponent, both your numerator and your denominator gets raised to that outside exponent. So an example of this would be if I had 7 over x to the 3rd and I squared that. That would equal 49 for 7 squared over x to the 6th because a power to a power. Again, you would interchange and mix and match some of these. Another example would be if I had 2 thirds x and I raise that to the 2nd. That would be 4 over 9 x squared. Everything gets squared. The 2 got squared, not 2 times 2. Well, I guess it turned out to be. The 3 got squared, that's why it's 9 and not 6. And the x to the 1st power is 1 times 2 is 2. Alright? Now, based on our quotient of powers here, we're going to discuss the negative exponent. And the idea comes from when you have a situation, which I'm not going to put anything in the red like I've done a lot of the other problems. But if you had a situation where you had 7 to the 10th power divided by 7th to the 15th power, when you subtract that, you're going to get 7 to the negative 5 power. 10 minus 15 is negative 5. You always do top exponent minus bottom exponent. Since this is in the numerator, and I know it's in the numerator because it's not under something, okay? I make this negative exponent positive by flipping it and putting it in the denominator. Okay? Now say flip it. I didn't take the reciprocal because I don't want you to think reciprocal here. Let me show you another example. If I had 14x to the negative 3 power, and I said I don't want any negative exponents, which most of these problems, they don't want you to have a negative exponent. The way you would simplify this is you would say 14 over x cubed. Notice that it became positive once it's down here. Notice the 14 stayed up here as well. It didn't move down to the bottom because the only thing that has a negative exponent is the x. Alright? Another example would be, what would you do in the instance that if you had something like 8 over y to the negative 4 power, that would equal 8y to the 4th, because that would move up. So what's the rule here? If you have a negative exponent in your numerator, you move it to the denominator. If you have a negative exponent in your denominator, you move that up to your numerator. In each case, then your exponent becomes positive. Now, these are the rules that and the properties that we will be working on and that you need to have a good handle on. They'll show up in different parts of each problem. For example, there will be a combination of some that fit together in certain problems, and you'll need to be able to look to recognize them. The name is not important as much as you being able to visually recognize the pattern in the problem. You actually have to put some work into it, because this will get even more complex when these m's and n's and 9s and 10s and stuff that you see become 1/2s and 2/3 and stuff. And if you don't have this stuff down, when the numbers get a little bit more complex, then your understanding is really going to be tested. All right. Have a good one.